Welcome to qnawire.
In this question, we are going to show why a quantum pencil can't be balanced on its point. We begin by solving the first item of this question, which asks us about why is this the case. So the situation is the following. We have a pencil, and that pencil has a weight force that acts on its center of mass, and that weight force produces a torque that will make that pencil rotate and therefore fall. This will happen unless we can make sure that the weight force is aligned with the pencil and at the same time that the pencil do not have any angular velocity. It might be easier to understand this idea by looking at a simple calculation. The torque that is produced by the weight force is given by the intensity of the weight force times the distance in between the point of the pencil and its center of mass. Let me call this distance r, times the sine of theta, which is that angle in green. If we can make sure that theta is equal to 0, then the torque produced by the weight force will be equal to 0. That is, the weight force will be aligned with the pencil. As a consequence, the angular acceleration of the pencil will be equal to 0. Look, the torque, the resulting torque, is equal to the moment of inertia times the angular acceleration. If that torque is equal to 0, then the angular acceleration will also be equal to 0. Therefore, the unstable equilibrium condition is given by theta equals to 0 degrees and theta dot equals to 0 degrees per second. This is necessary because the angular acceleration is equal to 0 and this is assured by theta being equal to 0. But if the pencil has some angular velocity, then it will just move out of its equilibrium position. So these two conditions must be satisfied at the same time. And this is a problem because quantum mechanically we have this uncertainty relation. That is, the uncertainty in the angular momentum times the uncertainty in the angle must be bigger than or equals to h bar. Then it can't be true that both of those uncertainties is equal to 0 at the same time. And this is precisely what this condition is asking for. For this condition to be satisfied, theta must be equal to 0 with 0 uncertainty, and theta dot must be equal to 0 with 0 uncertainty. And we know that the angular momentum is proportional to the angular velocity. Then this is the reason why a quantum pencil can't be balanced on its point. In the second item, we have to give an estimate for how long it will take for the pencil to fall if it is positioned initially as well as possible. We begin by solving the equations of motion for this pencil, and I'm talking about the classical equations of motion, and then we use quantum mechanics only to give boundary conditions. So let's begin by solving the classical equations of motion. For the rotational movement, we have that the torque is equals to the moment of inertia times the angular acceleration. We know that the torque is given by the torque of the weight force, which is the intensity of the weight force, times r times the sine of theta. And this is equals to the moment of inertia, which, considering that this pencil is a uniform rod, is given by 1/3 of the mass of that pencil times L squared. So on the right hand side we have 1/3 mL squared times the second time derivative of theta, which is the angular acceleration. Now notice that if the pencil is a uniform rod, then the distance in between the tip and the center of mass is just L over 2. So R is equals to L over 2, and we can write this equation as the weight force times L over 2 times the sine of theta is equals to 1/3 times the mass times L squared times d squared theta dt. As you can see, we can already simplify L on both sides. Now, the weight force is given by the mass of the pencil times the acceleration of gravity. So we have m times g times the sine of theta divided by 2 being equals to 1/3 times m times L times d squared theta dt squared. And now we can simplify the masses on both sides. So the equation of motion is given by g over 2 times sine of theta equals to 1/3 times L times d squared theta dt squared. Now let us reorganize this equation as follows. We will send this term 1 over 3 to the other side dividing and L to the other side dividing. The result is the following. Now we have 3 times g divided by 2 times the sine of theta, and we also have a factor of L here, is equals to the second time derivative of theta. Now, sending everyone to the same side, we have d squared theta dt squared minus 3 times g divided by 2 times L times the sine of theta is equals to 0. And this is the classical equation of motion for the pencil in this situation. Now note that this is a non-linear equation because the sine of theta is not a linear function of theta. In order to be able to solve this equation without using numerical techniques, we have to make a simplification. We have to assume that theta is very small, and when theta is very small, we can approximate sine of theta as being equal to theta. So, using this small angle approximation, the equation of motion is a linear equation that is as follows. Second time derivative of theta minus 3 times g divided by 2 times L times theta is equals to 0. To solve this kind of equation, we assume that theta is of an exponential form. That is, theta is given by e to k times t. And now we determine what is k. By substituting theta as this into this equation, we get the following. The second derivative with respect to t of this quantity is given by k squared times e to k times t minus 3 times g divided by 2 times L times a to k times t. And this is equals to 0. By factoring a to k times t, we get the following. E to k times t times k squared minus 3 times g divided by 2 times L is equals to 0. We know that this will never be equals to 0. Then, we can just send it to the other side dividing. By doing that, we are actually simplifying this calculation, so we end up with the following. The solution is this one that we proposed, e to k times t, provided that k is given by plus or minus the square root of 3 times g divided by 2 times L. Now that we know the solution, let me organize my board. Okay, so we have two solutions. Which one are we going to use? Well, in general, we use both of them. That is, in general, theta as a function of t is equals to some constant a times e to plus the square root of 3 times g divided by 2 times L times t plus some other constant b times e to minus the square root of 3 times g divided by 2 times L times t. Generally, in order to evaluate a and b, we would need two boundary conditions, but we can use some heuristics here so that we eliminate one of those. We know that the pencil in our situation is falling, and as the pencil falls, theta will increase. So we want the theta of t function to be an increasing function of time. And as you can see, this is a decreasing function of time. Therefore, this will not describe our situation. In other words, b is equals to 0, and the function theta of t that suits our needs is the first one. So it is equals to a times e to plus the square root of 3 times g divided by 2 times L times t. But this is a function theta of t, and we want to calculate the time it takes for the pencil to fall. For that, we will need a function t of theta. To get that function, we have to invert this one. We proceed as follows. Send a to the other side dividing, so theta over a is equal to the exponential of the square root of 3 times g by 2l times t, and then take the logarithm of both sides of this equation. So we will get the following. The logarithm of theta over a is equals to the square root of 3 times g divided by 2 times L times t. Then send this term to the other side dividing. Then we get the following. T is equals to the square root of 2 times L divided by 3 times g times the logarithm of theta divided by a. This equation tells us that when the angle is theta, the time is t. Then how much time does it take for the pencil to fall? The answer is the following. That time, let me call it capital T, is given by t when theta is equals to pi over 2. that is when the pencil is lying flat on the table, when this angle is equals to pi over 2. In this situation, capital T, or the fall time, is given by the square root of 2 times L divided by 3 times G times the logarithm of pi divided by 2 times A. So we are almost ready to get a numerical answer, but before doing that we need to know what is the value of this constant A. Before doing that, let me organize my board yet again. Okay, to determine this constant A, we have to use the uncertainty relation. This relation tells us that the uncertainty in the z component of the angular momentum times the uncertainty in the angular position is bigger than or equals to h bar. We know that the angular momentum in the z direction is given by the following expression. It is the moment of inertia times the angular velocity. The moment of inertia is an exact quantity, so any uncertainty must be here. Then, the uncertainty in the z component of the angular momentum is given by the moment of inertia times the uncertainty in the angular velocity. Then we have the uncertainty in the angular position, and this must be bigger than or equals to h bar. Now, using the expression for the moment of inertia that we already know, we get the following. The uncertainty in the angular velocity times the uncertainty in the angular position times the mass times L squared divided by 3 is bigger than or equals to h bar. Now we go back to this equation for theta as a function of time just for a moment. Note that theta of 0, that is the initial angle, is equals to A. At the same time, notice that the angular velocity, omega of t, which is defined as d theta dt, is given by A times the square root of 3 times g divided by 2 times L times e to the square root of 3 times g divided by 2 times L times t. Then, initially, the angular velocity was A times the square root of 3 times g divided by 2 times L. Now notice the following. Initially, we would like, ideally, that theta of 0 to be equal to 0, which would imply that A is equal to 0. But this is not possible because of this uncertainty relation. Therefore, we say that theta of 0 is equal to 0, but it has some uncertainty, delta theta, and that uncertainty is exactly equals to A. Then, from this, what I'm saying is that A is equal to the uncertainty in the angle, so delta theta is equals to A. At the same time, the uncertainty in the angular velocity must also come from the uncertainty in A, because we want the angular velocity to initially be equals to 0. But again, this is not possible because of this uncertainty relation. So we use the most precise case that we can achieve, which is saying that omega of 0 is equal to 0 plus some uncertainty, and that uncertainty is precisely given by this equation. Then, this is the uncertainty in the angular velocity. Using these equations, we get the following. A times the square root of 3 times g divided by 2 times L, which is delta omega, times A, which is delta theta, times m times L squared, divided by 3 is bigger than or equals to h bar. Now we solve this equation for A. We get the following. A squared must be bigger than or equals to 3 times h bar divided by m times L squared times the square root of 2 times L divided by 3 times g. Then, taking the square root, we get that A must be bigger than or equals to the square root of 3 times h bar divided by m L squared times the square root of 2L divided by 3 times g, and this is under a square root. So A must be at least equals to this value. Now we know what is the value of A. Then we can finally finish this question. Before doing that, let me organize my board again. Okay, now all we have to do is plug in all the values that we have and finish the calculation. So the time it takes for the pencil to fall is given by the square root of 2 times L, which is 18 centimeters. Let me convert to meters by multiplying by 10 to the minus 2, divided by 3 times the acceleration of gravity, which is approximately 9.80 meters per second squared. Then we multiply this by the logarithm of the following. In the denominator, we have 2 times a, but a is given by the square root of 3 times age, which is 1.055 times 10 to minus 34, divided by the mass of the pencil, which is given by 7 grams. Let me convert to kilograms by multiplying by 10 to the minus 3, times L squared. L is 18. We convert it to meters by multiplying by 10 to minus 2, and then we square it according to the equation for A. Then we have to multiply this quantity, still under the square root, by the square root of 2 times L, which is 18, but we convert to meters by multiplying by 10 to minus 2, divided by 3 times g, which is the acceleration of gravity, so 3 times 9.80. Under a square root, under another square root, and finally in the numerator we have pi. Now by solving this calculation, we get a time that is approximately 3.97, and then we can further approximate this result to 4 seconds. And this is the answer to this question.